Hello and welcome to video number 5 in our series of looking at the most accurate clock on Earth. You may have noticed on the thumbnail that I've improved the new pendulum and bob setup, and basically I've had to do that to overcome some of the problems we were having with our confusion with vectors. Now basically, if you just remember that, going back to that last video number 4 and the one that's number 3, the universal joints allowed us to identify vectors, and obviously the first vector that we knew about was the one that swings in the same direction, the swinging direction, but looked like we were detecting other vectors coming from the left or right or wherever, and they were very hard to identify without those universal joints. But with the universal joints it was clear that there was a vector coming from the left that was not the rotation of the Earth, because it was exaggerating the counterclockwise direction more than what we were expected from the Earth, which looked like clearly it was some imbalance in the bob. Now I've readdressed that with the new design. So the new design basically covers these major points. It can be balanced. That's the number one thing I found. It has to be able to balance. We just cannot rely on making a bob and hoping that it's going to be true straight off the lathe. Although that last bob, as you know, that was extremely small run out, that glass bob, still it was unbalanced. I'm going to go on to a magnetic release. I'll show you that as we see the video, the demonstration. I've cleared that up. It's cheaper to make. The bob is now going to be cheaper to make. It's just made from a cue ball, which it can be obtained anywhere, and they're cheap to make. Less fragile. That glass bob was really, I tell you, I was always on edge. If it was to fall, break from its cabling, it would have been disaster. And the big one now is I'm able to launch it from different directions. So although we know that the pendulum, according to Foucault's instructions, it must be launched north-south for initial launch all the time. However, it would be nice to be able to launch it east-west and north-south, east-west, whatever, but we have to abide by his original formula, and that's got to be north-south. But with a few tricks, I've allowed us to launch in different directions, which I'll show you again. Also, before we go on to show that pendulum, the demonstration, just going over our formula. The new formula gave me a huge breakthrough. It's probably the biggest breakthrough I've come through yet with my new formula. Basically, the existing formula was this: the period of a pendulum is equal to 2 pi, the length of the pendulum over gravity, the square root of that. Now, my formula was to remove gravity. I was thinking, how am I going to remove gravity out of this? I don't believe we need gravity to make this thing work, which I've been trying all along. If you remember that initial where I tried to use my little, where was it? The tuning fork setup. I forget how many videos back that was, but it doesn't rely on gravity. Now, I believe we can use something like that. Although, it's still my intention to keep tracking with the Foucault pendulum. I don't want to break away from that. I do want to take off on other tangents, of course, which will be the clock. I still want to go on that tangent, but keeping our original trueness to the great man Foucault. I still believe, although he frustrates me at times with his engineering, I think we should follow his and crack this pendulum and see whether it actually shows this Earth spin or not. Although we can use new materials and new advanced technology, but we still must keep true to his concept. So now my new formula was now T is equal to 2 times the square root of L, which was removing gravity. Now we just can't remove gravity out of this formula and end up with the same period. So what I did was, as you know, I realised was, so many videos back, I can't remember, we know that the pendulum in this falling state virtually has no gravity. So we know that there are no weight on the bearing. The bearing is now in a position where it's no weight on it, which is what we want. That's what we want. We don't want no weight on that bearing. However, on the upswing, we do get weight. And we get twice as much, because now not only is it going against normal gravity, but it's actually accelerating against it. So that's our problem. We have to remove gravity somehow out of that. So this is what this formula of mine did. And in fact, if you use this on Earth, you'll get within plus or minus 10 milliseconds of anywhere on the gravity of Earth. So this formula here, if you want to use it as shortcut, it will give you accuracy of 10 milliseconds plus or minus 10 milliseconds, which is, you will never be able to measure that difference with a pendulum. No pendulum ever been constructed to give an accuracy of 10 milliseconds. So what we found was that the pendulum has four states, which it looks like the original people who derived the formula made a somewhat of an error, because what happens is the pendulum has this state. It falls with zero gravity and then it rises with twice the gravity or twice the force, cancelling it, comes back again in a fall state, back to a rising state again. So the period is 4 sections, 1, 2, 3, 4. And that is our problem. We don't need gravity to make this thing work. We can actually have two springs. Now we can have a spring here on a system and a spring here on a system, and we can make this thing oscillate. Now we don't have to catch the form. We don't need the period anymore. We can make this thing go really fast, as you might have seen on the lathe. Remember the lathe, that piece of rod? It wasn't to any formula with the relation to gravity, or it was oscillating independent of gravity. So that's what we've got. Although this formula will show accuracy to plus or minus 10 milliseconds, if you want to use the period of a normal pendulum, we don't need it. We can make this thing oscillate. And I can have different tuning forks now. We can progress to another type of pendulum with this tuning fork system, and we can replace the pendulum with that. But still, remember, I will keep faith to the Foucault's design. So I'm not going to break away from that. I think people had this fear that I was going to break away from the pendulum. I'm not. I'm going to take different tangents to prove it from different directions. So, that being said, we'll go and do the demonstration now of the pendulum. That's what you're obviously wanting to see. But quickly, just on the clock thing again, remember that we are also doing the clock. So, I did notice this. This was a very strange thing. Now, if you know anything about these laboratory clocks, in the early 1900s, there was no way, well, this is way before atomic clocks and crystal clocks and crystal oscillator clocks, the laboratory clocks needed accurate timing. And a gentleman by the name of Schoft, I think that's his name, Schoft, he made a very accurate clock, a pendulum clock, and it was called the Synchronome clock. Very accurate, look that up on YouTube. Brilliant bit of work. He had counteracting, he allowed mercury field pendulum, and he did some really clever tricks to get his accuracy. But he did not use one thing. Now this is the intriguing thing that actually amazed me. He could have, and he did, actually use a rigid pendulum rod. He didn't use a cord like a cable like Foucault, but his bob was also rigid to the pendulum shaft. So he never thought about the torque from the, like this bob here, mine has a bearing in it, right? So it can twist. So it, in fact, if it was to be used in one of these synchronome clocks, it would have actually allowed for the torque of the twist of the earth. Because this is what this gentleman was into. He was into extremely accurate measurements using a pendulum clock. But he didn't count for the twist in the earth. Interesting. Okay. All right, let's go now to the demonstration of that. I'll give you, this is supposed to be an introduction because this is quite a long experiment and there's quite a lot of work goes into this. So quickly, let's go into our demonstration now showing that pendulum. Okay, so here we are with our new bob arrangement, and to our left is the magnetic release mechanism. Down there on the floor is the magnetic release controller, which is a pulse width modulator, which just gives me enough magnetic coupling to capture the bob. Over here is our laser set up again as normal, and going up to the ceiling, our illuminated cable all the way up. Continuing all the way up. To our mounting at the top. Now here's the thing that's a little bit different. The mounting now no longer has any bearing. It is straightly connected to the cable itself. So the cable now is the actual bearing. So it must swing and take the function of the swivel bearing and magnetic coupling that you would have seen before. The reason for that is I can now turn the bob in any direction and it will actually track position of the cable. So with the swivel system it just would swivel around and do its own thing. But now it's actually locked to a fixed datum point. So here's our setup. The bob has 4 outriggers, colour-coded black, blue, green and red, which can be removed. And a grub screw can be replaced to tune them internally to remove any imbalance in the bob. This stage I'm just showing this for demonstration, to show a few concepts, but there's a ball bearing on the end which locates into a divot in the magnetic coupling, allows it to steady and swing in any direction. The bob is white, which helps illuminate the laser a bit better, and this is a demonstration, introduction. I won't go too much detail. I'll just do a quick launch and show you the advantage of this magnetic coupling. So we charge the magnetic coupling with just enough to hold the bob and let it settle. Okay, I've got that a little bit adjusted, a bit high, but it'll show you anyway. It's quickly settled down. If you remember, with the string was holding the bob, the string launch mechanism, the bigger disadvantage of course of that was that it could only be launched from one direction, but it took forever to settle. And this is almost instant, so just quickly release the magnetism and we have okay, there's a slight wobble there, which I'm not too happy about, obviously. As I said before, my magnetic coupling is a little bit high. But the other thing we might notice is that the bob has swung slightly around. Now I'll just reposition and we'll launch from the green now. Alright, I've swung the bob around 180 degrees, we're launching from the green. So now this is the black over this side. Okay, now the camera's obviously blocking that laser, so I'll just move that out of the way. The advantage of the white is you can see the laser on the bob easier now, and we can actually watch the laser track around the bob as it moves clockwise or anti-clockwise. Just let that run for a bit. I'll line that up with the camera and the laser now. That just happened to drop straight on that line. Let's just let that run. We may have to go 5 minutes to see anything. Again, the bob is twisting. We shouldn't see that. That's a no-no. As we said before, the bob must never move. It must never twist. It must stay in exactly the line of launch, which is a big advantage of having these outriggers. So clearly this bob is out of balance. I'll probably have to tidy up the camera because where I'm looking now blocks the laser across the front of it. But you might notice that the laser is starting to drift across the front of the bob. It's not hitting the centre anymore, it's a little bit out. Okay, look, this was just a demonstration for the introduction. I don't want to go too long. This video is getting too long now. The next videos will be showing you the launch from the 4 directions, and you'll see what will happen when the bob is out of balance. You'll see the effect that it'll go clockwise, anti-clockwise and straight ahead, depending where it's launched from and how it's positioned. Which I know this is quite controversial because this is what a lot of people debunking the Foulkes pendulum state, that the pendulum can be tuned to actually track clockwise or anti-clockwise. However, we must always experiment and show that it can also be counteract as well. So that's the objective, is to prove Mr. Foulkes. Alright, so I think we'll see that pendulum starting to drift way out now. It's also doing an elliptical orbit, which that's number one giveaway that the thing is out of balance. Okay, thanks for watching. I think that's enough, and hopefully in a week I'll start doing some more close-up experiments. Thanks for watching.